All right, here in chapter 13, we've been talking about different states of matter, sort of like what makes them the way they are. We started off with gases, and we talked about how the gas particles are constantly in motion, bouncing off of each other, and they really don't stick together because we assume that those intermolecular forces, those attractions between the particles, well, we're going to assume in a gas don't really exist. Okay, they're there, but we assume that they're moving so fast that they can't really stick together. But now that we're talking about liquids, that's a little different. Okay. So we're going to assume that liquid particles are generally moving slower than gas particles. And then if they move slow enough, those attractions are going to start to take over, right? And they're going to start to come together. So in this picture here, you can see this is a gas because the particles are further apart. But in a liquid, they're being attracted together. Now, maybe not as attracted together and orderly like in a solid, but certainly more than a gas, right? Okay, so we can no longer ignore these forces of attraction, these intermolecular forces, like we could when we were talking about gases. Now, we know a liquid could become a gas if it evaporated. Right? So you guys have known this for a long time, right? We can have a liquid. Remember, I said liquid. I didn't say water. Water is just one type of liquid. A lot of people, as soon as they hear liquid, they start picturing water, and that's all right. But I just want you to keep in mind that we're talking about all liquids, any liquid that you could ever think of. They all follow the same basic rules, okay? All liquids can evaporate into a gas. How could they do that? Well, they would have to start moving fast enough. The particles that are in a liquid that are moving faster than the others may have enough energy to break away from the other's attractions and then move out as a gas, okay? So when that happens, right, the ones that are moving the fastest are the ones that are leaving. Therefore, the liquid is actually losing its highest moving particles. So liquids actually start to cool down as they evaporate, because the ones that were moving the fastest, that were keeping their temperature up, are the ones that are the leaving in evaporation. Now, this works really well when we talk about why do we sweat, okay? What's the whole point of sweating? So let's say you're doing something athletic, or you're working out or something like that, right? And you start to sweat. And these beads of sweat are on your forehead or in your armpits or wherever, right? You've got sweat coming out of all sorts of places. And why does your body do that? Okay? It's doing that simply because it knows that if it puts a little bit of this water that you have inside of you on the outside of you, that the particles that are moving fastest, the hottest of those liquid particles, will start to leave. And as they leave, the only thing that's going to be left is cooler water. And of course, if you have cooler water on the outside of you, hey, that's better. And where are those particles getting their high energy from? Where is your sweat getting all of its heat energy from? Well, from you, because your temperature is up so high. That's why you start to sweat. Okay? So your body, that's your response to it. It knows that evaporation is a cooling process, because as it evaporates, those particles of the liquid that are turning into a gas are the ones that are taking away most of the energy. The other thing that we have to realize is that as a liquid starts to evaporate, the particles of gas can actually accumulate and start to create a pressure. We call this vapor pressure. Okay? So if we have, let's say that we have a beaker of water that's sitting in a jar and this jar is sitting over the top of it. Okay. So now, the water particles that are in this water could leave. Some of them could start to have enough energy that they leave and start to make water gas, water vapor, right? And this could happen more and more and more and more. And more of these particles would start to build up. Now they can't leave because this jar is over the top of our beaker. And so all of this water vapor that's in here starts to build up pressure. And it builds up and it builds up and it builds up, and that's what we call the vapor pressure. The higher the temperature of the particles, the faster they're moving, and the more of them can evaporate. So vapor pressure is sort of like measuring the evaporation rate of something. The higher the vapor pressure, the more evaporation is happening. Okay? Eventually, you might have so many particles of gas in here that no more of these particles of liquid can actually start to evaporate and create even more pressure. Okay? The pressure is too great. And so generally, if this were to happen, if I had a jar over a beaker of water, for instance, only some of the water would evaporate, not all of it. Now, if we took this jar off of the top, we took this container off the top, and we'd let these particles of water vapor just go out into the big air of the room, then you could probably get all of this to evaporate because the pressure wouldn't build up in this little space. So you can see what happens to the vapor pressure as the temperature goes up, right? If we keep increasing the temperature, let's say, of this water, okay, for example, notice how the vapor pressure keeps increasing, okay? Now, what's interesting is right around 100 degrees Celsius, and we know something really special about 100 degrees Celsius, right? What do we learn about 100 degrees Celsius? It's the point at which water boils, right? So if we get the temperature of water up to 100 degrees Celsius, look what its vapor pressure is. 760 millimeters of mercury. Now, doesn't that also seem familiar? In the last lecture we just talked about, 760 millimeters of mercury is equal to normal atmospheric pressure, the normal pressure that you're normally in all of the time in the air. So the vapor pressure of the water builds all the way up, and then at 100 degrees of the water, it has a vapor pressure that's equal to the atmospheric pressure. That's going to be really important here in just a minute. Now, boiling. We've talked about this before, right? Boiling, we know, is the liquid turning into a gas. So how is it different than evaporation, which is also liquid turning into the gas? Well, the difference is evaporation is only a few of the particles of liquid were moving fast enough to leave. Boiling means all of the liquid's particles have enough energy to all break free at the same time. And they can do this because the vapor pressure of that liquid is equal to the atmospheric pressure. Liquids always boil when their vapor pressure equals their atmospheric pressure. So water's vapor pressure at 100 degrees Celsius is 760 millimeters of mercury. So if you're trying to boil water in a room that has normal atmospheric pressure, which is about 760 millimeters of mercury, then that water will boil at that point. So that's why we say that water boils at 100 degrees Celsius. Now, what if you're not sitting in an area where the atmospheric pressure is 760 millimeters of mercury? What if you're, okay, let's say that you're living high in the mountains. And it's the further you go up into the mountains, the less the atmospheric pressure is, right? Because you're going higher up into our atmosphere, the less air there is up there. So the less atmospheric pressure there is. Would you need to get your water up to 100 degrees Celsius to get it to boil when you're living in the mountains? No, you wouldn't. Let's say that your pressure up in the mountains is only 700 millimeters of mercury instead of 760. The water's vapor pressure is going to reach 700 millimeters of mercury before it gets to 100 degrees Celsius. It'll do so at a lower temperature. So when we say that the water's boiling point is 100 degrees Celsius, we call that the normal boiling point because it's normally where most people are going to be located in terms of pressure. Normally, most people live in a pressure that's close to 760 millimeters of mercury. Not everybody, but most of the time. So that's why we call it the normal boiling point. So boiling is dependent on two things: temperature and pressure. Now, normally you can't change the pressure of your room. So normally we don't even worry about that. We assume the pressure is going to stay the same all the time. And so the only thing that we change about our liquids is their temperature. But you could boil a liquid using just pressure changes. In fact, if you guys remember, okay, bring this up when we're talking about this kind of stuff in class, and I will show you a demonstration of being able to boil water without heating it. Okay? It's kind of interesting. Most people don't get to see that. So again, what's the difference between evaporation and boiling? Evaporation is liquid turning into a gas, but only the fastest ones at the surface can leave. Boiling means all of the liquid particles are moving fast enough to leave. All of them want to leave at once. In fact, some of them even down here at the bottom try to leave, and that's why we get bubbles when boiling occurs. The ones down here in evaporation means that these particles of liquid are not moving fast enough, and that's why you don't see bubbles down here. You just get a little bit of the particles up here to leave, and that's evaporation. So I don't know how many of you have ever seen anything like this, but you can actually cook using something called a pressure cooker. You may have a device at your house that does this, but pressure cooking just simply means that we enclose all of the boiling water so that the pressure builds up. And if the pressure builds up, we can actually get the temperature of the water to actually have to boil at a higher temperature. So you might not get the water to boil until, well over 100 in a pressure cooker, which means you can cook things faster because the temperature's at a higher temperature. Right? Something to keep in mind when we're talking about boiling, it's not just temperature, it's also pressure. Now, solids, the last of the three states of matter that we're going to talk about, right? Solids are different because the solid particles are generally moving even slower. So now we've really slowed down these particles. So they're still moving. Probably we would call them maybe just vibrating in place. And they're much closer together because those intermolecular forces, those forces of attraction are really pulling them in. Kind of like our little magnetic marbles. We're really being held together by the magnetic force. Okay. So this is how we picture most solids. They're moving just slightly, but they are being held together, usually in some kind of orderly fashion. If they are in an orderly fashion, we call them crystals. Most solids are crystalline. Right? And I know right now your brain is thinking, crystals? Oh, aren't those really shiny, pretty things that people make jewelry out of and whatnot? Well, those are one type of crystal, but almost every solid that you see around you is a crystal of some kind. Okay? If you're writing things with a pencil right now, I guarantee you that the pencil lead that you're writing with is a crystal. It doesn't look shiny and pretty, but it's a crystal because the particles are arranged in an orderly pattern. That's all the word crystal actually means. The smallest group of particles within a crystal that still holds the shape of the crystal is called the unit cell. If you recall, we had an activity where you were looking at salt crystals, right? You saw those salt crystals, and they had sort of cubic shapes to them. Right? You can see sort of a big cubic crystal here. Well, if you were to take this cubic crystal that you can see with your eyes, and then you were to kind of be able to use some kind of super microscope where you could see really, 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 really close up in it, you could see the individual particles within this crystal, they would also be in a cubic shape. They'd be lined up in a cubic shape, and that's why the overall shape is a cubic shape. Now, do all crystals have to be cubes? No. There's lots of different shapes they could be. You do not need to know them all. But I do just want you to keep in mind that there are lots of different shapes. Now, not all solids are crystals. Okay, so if the particles are not in an orderly pattern, then we say that that solid is amorphous, which means without shape. Okay, glass, plastic, silly putty. Okay, those would all be examples of amorphous solids. Solids that actually do not. That doesn't mean that you can't form them into shapes, right? Glass we can make into lots of different shapes. But if you were to look really, really closely, if you could see the individual particles in glass, they do not line up in a nice, neat pattern. In fact, that's why it's really easy for glass to be bent once we heat it up a little bit, bent into lots of different shapes.